So we left off with this problem last time, the simply supported beam, and we found the reactions. You got to find the reactions on the thing. Summing the forces in the horizontal, we found that R3 is equal to 0. Most people could probably do that by inspection. And then R1 and R2 were both P divided by 2, that load divided by 2, because it was symmetrical. And then we said we were going to have to take a section through here. We're going to take a section there where X was between 0 and L over 2. And then we're going to have to take a section in here where X was between L over 2 and L. And when I did the first section, we're using our deformation sign convention. We had the reaction here. This was equal to P over 2. This distance now is X. And then we just had to flat memorize that the shear is acting down and the moment is counterclockwise. And I've drawn those away just for clarity. Those are actually acting through the cut point or the intersection of that. Did we have anything else there? I think that was it, wasn't it? And then for this one, we continued. We got a couple ways, and we'll maybe tackle the other way, but initially we continued to go from the left-hand side, where now we had this load P there. We had the reaction, still P divided by 2. This distance is X. This is L over 2. And we have the shear acting down, and the moment, again, counterclockwise. So my task then, as I left off last time, was to come up with the shear. So if I sum the forces in the vertical direction here, setting that equal to 0, what do I have? I have P divided by 2, that's acting up, minus V, so we can conclude that V is equal to P divided by 2. Okay. Is that right? Good. Okay. And then if I sum the moment, you can sum the moment about any point that you want. I tend to sum it about the cut point where I cut through, because then I don't have to worry about V, and if I happen to have made a mistake on V, it's not going to carry through. Because remember, I've only separated this for clarity. The shear force actually acts through that plane of that cut. So if I sum the moment about the cut, I'm going to have the moment M, that's a free vector, that has to be added in. And then I'm going to subtract off P over 2 times the distance that acts through, which is X. So I can conclude that the moment is equal to Px divided by 2. So that's that one. Then I can go over here and do the same thing. Here I sum the forces in the vertical direction, setting those equal to 0. I have P divided by 2 minus P minus V. And V then we conclude is equal to minus P divided by 2. Okay. Well, again, sum the moment about the cut. And like I said, I just do the cut out of habit. It's also nice, then I don't have to worry about if I've made a mistake with the shear force. It's not going to propagate through the problem. So summing the moment about the cut, I will have M and then plus P times this distance here. What's that distance there? X minus L over 2, is that right? So those are both going in the counterclockwise direction, and then I'll have to subtract off P divided by 2 times the distance X that acts through. Is that all of it? I think that actually is. So I could say then that the moment M is equal to P times L over 2 minus X plus Px over 2. Bringing that negative sign through, I think I'm okay. So I have PL over 2 plus Px over 2 minus Px. So we get PL over 2 minus Px over 2, or we could say that that's P over 2 times L minus X. Okay on that? That's good. Now the question might come up before I go to step number 3 and start drawing it. Could we have come from this other side? Could we have looked at that piece there? And the answer is absolutely. I think I'll start that on a separate piece of paper. Any questions before I do that? So if I wanted to look at an option, we would say, or for x between L over 2 and L, I could have looked at the right-hand side. And that would have put the reaction here. This is P over 2. I would have then, by the deformation sign convention, I would have had the shear going up. And again, you just unfortunately have to memorize that. You've got the moment going that way. And then probably the trickiest part to this is this distance in here is going to be what? L minus x, isn't it? Okay. So now if I sum the forces in the vertical direction, setting those equal to 0, I have V acting up plus P over 2 acting up. I solve for V is equal to then minus P divided by 2. And that is the same as what we had with this. So that's good. And then if I sum the moment about, you could do it about any point, but again I'll do it about the cut. We'll say that we have m minus p over 2 times the distance that acts through, which is L minus x. So we could say that m is equal to p over 2 times the quantity L minus x. Is that what we got before? Yeah, quite a bit easier that way. So sometimes doing it one way or another gives you a little less algebra, a little more algebra. Don't be worried that you're going to do a wrong one, because if you pick a so-called wrong one, you're only going to have to do more work. You should still get the correct answer if you're careful. Although a lot of times if you have to do a lot more algebra or something, that opens you up to mistakes. So we've got these pieces, so we're ready to go ahead, and step number 3 is then do the plot. So we typically redraw the beam, put my reactions here. We had the reactions, this one we knew was 0. This one was P over 2. This is P over 2. We had the concentrated load, then P at the center. And we could come up with the shear and moment diagram. And like I said, this is not very intuitive, so that's why I want to use this step method. Here's our shear. We're working in abstract, so we don't have any units. And here is the moment, so the internal shear force and the internal bending moment. So for the first part of this thing, I'm going to use these equations, right? The shear is equal to P over 2. So there is P over 2. And then in the second part, I use the shear is minus P over 2. So there's minus P over 2. So I have a shear diagram that looks something like that. Now for the moment, I'll use the moment equations. For the first one, I use this equation here, px over 2. So if I start out at 0, I get 0. And if I start out at the center, this is equal to L over 2. If I look at L over 2, so I put px over 2 and I put L over 2 in there, I'm going to come up with what? PL over 4, is that right? Okay, and this is pretty common. That's probably one you want to remember. It's a linear equation, so it'll be a straight line. And then the other equation that I'm going to use, whether I go back to the last page or I use it from there, it's exactly the same equation. When you put L over 2 in there, you get PL over 4, and when you put L into here, you get 0. And it's a linear equation, so we get something like that. Which hopefully makes sense. I think we'd recognize that we probably have some of the largest stresses at the center of that thing. Certainly the largest bending stresses, therefore the largest bending moment. Questions with that? Now this is going to be very important when we start looking at stresses. We're going to talk about shear stresses. Shear stress tau is going to be equal to VQ divided by IB. We don't have to worry about too much of that, but if you can't get V correct, you're not going to get the stress right. And then our bending stress is going to be equal to minus my divided by I. And if we can't get M correct, it's going to be a rather hopeless process. So that's why we make a big deal about this. Yes?
At the point exactly in the middle, at L over 2, there's a maybe an acid curve. But what happens, in real life at that point. That want to say the internal shear is equal to 0.
Oh, right here, at the center. Yeah, there's a discontinuity. So we don't like to work. We don't like to look at that too closely. Okay. Yeah. Technically, we would have 0. Other questions? I guess the math people would spend a lot of time worrying about that. I wouldn't, because if I have failure in shear, I know it's going to happen somewhere in here or somewhere in here. Okay. So what happens right at the center, I don't get too worried about. Other questions? Except right at the center at the moment, I know that's where I have maximum moment, so that concerns me.
That's not going to be right through. That means that be at that point. Be at that little point.
Oh, that's a little different. We're starting to build a bridge to the moon or something with that. So it's a discontinuity. Other questions of that? Okay, so all these pieces are important. Let's try another one that comes up quite a bit, and that is a simple distributed load. If we look at maybe one of the beams in the floor underneath us or in the ceiling above us as it gets loaded up, it could well look like this. I want that to be a triangle. And we'll put a distributed load there. If you're using Timoshenko's textbook, he liked to use Q for the distributed load. We'll go ahead and use W for the distributed load. And we'll say that this has some length L. Okay. So if I do my free body diagram for this thing, I'll have reaction 1 here. I'll say reaction 2 there. I'll have the reaction 3, and then I'll have this distributed load. Like that. And this is L, W. So if I sum the forces in the horizontal direction, setting it equal to 0, I have that R3 is equal to 0. If I sum the moments about, we could really sum it about any point, but why don't I sum it about the left-hand side, setting that equal to 0. I have W times L, that's the total load of that thing, times L over 2, because it's going to act through the center, isn't it? It's going to act through the centroid of that. And then I have to subtract off R2 times the distance L. So I could conclude then that R2 is equal to WL divided by 2, which hopefully makes sense. The total load is W times L. If we have W that's 100 pounds per foot and it's 10 feet long, we'd expect the total load to be 1,000 pounds. And if you were going to try and carry 1/2 of it, you'd have to hold 500 pounds. Then I can sum the forces in the vertical direction, setting those equal to 0. I have R1 plus R2 minus the total load, which is W times L. Well, I make my substitution there for R2, and I can conclude then that R1 is also WL over 2. So a lot of times we go through that process fairly quickly. You've seen it before in statics. It is very important to get those right, because without getting the reactions right, it's hopeless from there. But so don't take me going through it quickly as meaning it's unimportant. It's just that we've done it before, and you should be comfortable with that. Well, I'm going to go ahead and take a section through this thing. I'll really only need one section, so I'm going to look at X somewhere between 0 and L. And I'll just go ahead and take the left-hand side and say this looks like this. So I'll have the shear acting down, the moment counterclockwise. Again, I've just memorized those. I won't put the 0 reaction in there, but I will put R1, which is WL over 2. This distance is, of course, X. So I have that distance X. Then I don't want to forget the distributed load. And we wouldn't want to try and turn that distributed load into a concentrated load, because that's really a different situation. Anyone that's maybe seen or tried to facilitate an ice rescue or something like that recognize that if you, instead of standing on the ice, if you lay down on the ice, it's a very different situation from a stress standpoint or a internal loading standpoint. So we don't want to try and change this distributed load into a concentrated load. We want to look at that concentrated load. We want to look at that distributed load. We don't want to look at it as a concentrated load. Well, let's sum the forces in the vertical direction, setting those equal to 0. What do we have? WL over 2, that's acting up, minus W times X, right? If this is W and it's going on for X, I have to subtract that off, and then I also have to subtract off V. So I can say that V is equal to what? WL over 2 minus WX, because V has a negative sign, I'll go over there easily. And I can say finally that V is equal to W times the quantity L over 2 minus X. Okay, so that's my expression for the shear. Let's see if I can come up with an expression for the moment. So I'm going to sum the moment about the cut point, setting that equal to 0. What will I have? I'll put M in there, and then I'm going to have plus W times L. And if we were to turn that into a concentrated load for finding the moment, it would be acting through the center of this, which is what? X over 2. So I have W times L acting at a distance of X over 2. And then I have to subtract off WL over 2 acting at X. So we could say then that the moment M would be equal to WL over 2 times X minus W. I think I've got a mistake here. I've got the moment M, that's right. And this should be W times X, shouldn't it? Yes, W times X, thank you. Okay. So I've got WL over 2 times X. That goes over with a positive sign, and this has a negative sign, so I have W X squared over 2, right? Okay. And you're way ahead of me on that, I think. I was recognizing that I was getting into trouble because I wasn't getting a second order term like I wanted. Okay. So we'll know the orders increase on this. This is linear. This should be a second order, quadratic. So if I tidy this up, what am I going to come up with? W over 2 times the quantity Lx minus x squared. Is that right? Yeah. We could have factored an x out of there, but I think, I mean, you could say this as, of course, Wx over 2 times L minus x is probably the way you'd see it in a math book. I'm going to leave it like this because I want to easily recognize it as a second order equation. But this other one obviously is a second order equation, but maybe not as glaring. Now, could we have looked at the right-hand side? Could we have come over here and said that we have this reaction here is still going to be R2, which is WL over 2. This distance is L minus X. Then I would have the shear acting like that, and the moment acting like that, and then I would have the load under here. So when I sum the forces in the vertical direction, setting those equal to 0, I would have V plus WL over 2 minus W times L minus X. Is that right? So that doesn't look too much more difficult, and we'd of course get the same answer. The next one, summing the moment about the cut point, setting that equal to 0 might be a lot tougher. We'd have the moment M minus, did I make a mistake? Yeah. I think, let's see, I've got the moment M minus WL over 2 times the distance L minus X. And then I would have to add to this W times L minus X times the distance L minus X divided by 2. So this expression here should net the same thing, but you're going to have to FOIL that out, and you got quite a bit more algebra ahead of you. Okay, so that'd probably be a good test for you. You know, take that home, play with that in your notes. I'm not going to take the time or space to do it here, but you should get the same answer. You should get this. You should get this for your shear. So there's nothing wrong with doing one direction or other. Sometimes one is just more difficult. Well, let's take these results that I have here for the shear and for the moment and plot those. So if I plot this, I always put the beam above it. And as we go into the shortcut method, that's going to be really important. So we have WL over 2 for the reaction there. WL over 2 for the reaction there. This one, of course, was 0. We have our distributed load of W, span of L. And we can come down here and we can talk about the shear and the internal bending moment. So if I use my equation, what do we have? WL times the quantity L over 2 minus X. Wasn't that what the shear was? So if I put X in as 0, what do I get? WL over 2. And this is the second time that the shear looks a lot like the reaction. Okay, that's going to be interesting when we get to the shortcut method. And then what if I put L into this thing? If I plug L into this thing, I have W times L over 2 minus L. I get minus WL over 2, right? Which again, negating the negative sign, it looks a lot like that reaction there, doesn't it? And we said that's a first order equation. It's going to be linear, so I will get something that looks like that. And if this distance here is WL over 2, and this distance here is WL over 2, just negative because it's going down, we'd know those are similar triangles, so this has to happen at L over 2, doesn't it? Okay, so that's going to be an interesting point as I go forward on this one. So now if I look at the moment equation, we said the moment was equal to Wx over 2 times L minus X. I think I had left this one, although this one's probably a little easier to plug things into. So either one of those. W over 2 times the quantity Lx minus X squared, or Wx over 2 times L minus X. So when I put 0 in there, I should come up with 0, shouldn't I? And when I put L in there, I come up with 0. It looks kind of boring, but I think this middle part, this L over 2, is going to be interesting. If you plug L over 2 in here, you come up with WL squared over 8. And that's an important point, probably worth remembering. WL squared over 8. Is that right? If we put this in there, so we're going to have WL over 4 times L over 1. We'll call it 2L over 2 minus L over 2, which is going to be WL over 4 times 2 minus 1 is L over 2, which is WL squared over 8. Yeah, that's great. Okay. Now you could do intermediate points. We know that it's second order. The question comes up, well, is it concave up or concave down? We're going to address that very quickly with the shortcut method, but to suffice to say, you could come in with intermediate points if you wanted to and work that out, and you'd realize that it looks something like this. Okay? Which, one important point is it's very different from this one, right? So when we have a beam that has a concentrated load at the middle, it produces a very different shear and moment diagram. So we don't want to think that we can take something like this and reduce it to something like this because it's easier. We get a different answer. We have to be careful with that. The other thing we've started to notice is we've started to see how these shear values are like the reactions here. And how this is a first order curve, linear, this is second order. And the other thing that's kind of interesting is if I look at this triangle here, let me go and look at this triangle that's right there. I have a triangle that looks like this, where this is L over 2 and this is WL over 2. So if I look at the area of that, I have WL over 2 times L over 2 times a half because it's a triangle. And what do we get? WL squared over 8, don't we? Have we seen that before? Yeah. So there appears to be some trends here that we need to take advantage of as we look at hopefully coming up with a shortcut method. Because I think if next week in our quiz we have a problem like this that we have to take 2 sections on, to do that in 5 minutes, we're all going to be sunk, right? Okay. So let's see if we can come up with a shortcut method. Any questions with these shear and moment diagrams so far? Everyone's good? So to develop the shortcut method, I'm going to look at a simply supported beam. You could do it with a cantilevered beam, but I'm going to look at a simply supported beam. I'm going to say we got something like this. And I'm going to orient a coordinate system. I'm going to say that this is x. And I'm going to say that this is W of x, so that's our load. And we could put a load on that looked like this. So you could have a constant or triangular, trapezoidal, sinusoidal, whatever kind of odd load you wanted. And I'm going to look at a point here at some distance x. I'm going to pull this section out. Okay? And this section, I'm going to pull out a section that is, why don't I say delta x. I'm going to slice out a section that's delta x. So let me pull that out and enlarge it quite a bit. Like this. So I've pulled that piece out, and there it is. And I'm going to say over here, let's see, that would be like if I was going to take the right-hand side of the beam, and the deformation sign convention says that the shear needs to go up and the moment has to go clockwise, right? Okay? So I'm going to call this the shear, and I'm going to call that the moment. And then over here would be like if I was looking at the left-hand side of the beam, and we know that the shear has to be down and the moment has to be counterclockwise. And I really can't call this M and this M both because they could be different. So why don't I do it this way? I'm going to say that this is V plus some change in V, could be positive or negative. And I'm going to say that this is M plus some change in M, could be positive or negative. So M plus delta M. Now I've already agreed that this distance here is delta x. And if we pull out this load, we've taken a portion of this load also, haven't we? So I'd better put that on here, and I'm going to put that on like this. I'll say that I have a load that's going to be equal to W of x times delta x. Okay. And then you might say, well, that would be in the center if it was a constant load. It would be at a 1/3 point if it was a triangular load. So it may not be in the center. So let me deal with that. Let me say that this distance here is going to be epsilon. We need another Greek letter times delta x. So epsilon would be equal to 0.5 if it was a constant. Epsilon would be equal to 1/3 or 2/3 depending on which way the slope was if it was triangular. So that's what we have going with that. So I'm going to take that piece and I'm going to do just like what we've done before. I'm going to sum the forces and I'm going to sum the moments. So if I sum the forces in the vertical direction, setting that equal to 0, what do I have? I have V acting up, so I'll take up as positive. So I have V acting up, and then I've got to subtract V and subtract delta V. So this is acting up, that's acting down. Anything else acting down? Yeah, minus W of X times delta X. Okay. So I've taken care of those three forces. So I can say then that delta V is equal to, solving this equation, delta V, because the V's cancel, is equal to minus W of X delta X, right? And if I could say, if I wanted to, then that delta V over delta X is equal to minus W of X. And if I take the limit, as delta X goes to 0, we'd come up with dV dx is equal to minus W of X, right? So what does this really say in plain English then? Well, dV dx, we oftentimes think of that as the slope. That'd be the slope of the shear. So the slope of the shear is equal to what? Minus the value of the load. So if I know the value of the load, I put a negative sign on it, and that gives me the slope of the shear at that point. Okay. Well, that's good. Let's see if we can come up with a similar conclusion for the moment. So I think I'm going to sum the moment about this point here because I have this distance there. So I'll call that O since we have two cuts. So we'll sum the moment about O, setting that equal to 0. And what do we have? I'll say that I have M plus delta M. So apparently I'm taking this way as positive, which is fine. You could do either way. So I've got M plus delta M. Now I don't have to worry about that one because that's intersecting the point, right? This distance here, I've only drawn that for clarity. So that would be 0. So I've got M plus delta M. And then I have to add to that W of X times delta X times the distance epsilon times delta X, right? So I've taken care of this one. This one is 0. I've taken care of this one. Let's see, this is a free vector, so I better subtract M. And I'm also going to have to subtract V times the distance that acts through, which is delta X. Have I got all of them? I think I've done that, and I've done that. I think I have. So now this one and that one cancel. I can bring delta M to the other side, so I have delta M is equal to V delta X. That would be positive. And then I have a minus W of X times epsilon times delta X squared. And I'll divide everything by delta X, so I get delta M over delta X is equal to V minus W of X times epsilon times delta X. And again, I'll take the limit as delta X goes to 0. So what do we come up with? dm dx is equal to V. This epsilon term, that's why I was fairly casual about what I did with that, doesn't matter because it's a higher order term. Okay. So what this says then in plain English is that the slope of the moment, the slope of the moment diagram is equal to what? The value of the shear. Okay. So the slope of the shear is equal to minus the value of the load, and the slope of the moment is equal to the value of the shear. Well, I'd like to come back to this equation here and this equation there. So let me move on to another piece of paper unless there's questions. Okay with that? So I had that dv dx was equal to minus w of x, and I also had that dm dx was equal to the shear v. So let me rearrange this a little bit. I could say that dv is equal to minus w of x dx, and then if I integrate both sides, when I integrate both sides on this, I come up with the, let's see, integral of dv is equal to v, isn't it? Is equal then to minus the integral of w of x dx. I guess we should say maybe this was the delta v probably. So this would be what? The change in the shear. In plain English, we could say that this is change in shear. So the change in the shear is equal to what? Minus, what do we think of with the integral? Yeah, area under the load. Okay, so the change in shear is equal to the minus the area under the load. Over here we'll do the same thing, so I could rearrange this. I have dm is equal to v dx, integrate both sides, and I get delta m is equal to the integral of v dx, where in plain English here I get the change in the moment. Change in the moment is equal to the area under what? The shear? So with these, we'll say this is the fourth one, this is the third one, and then back here, this is our second one and our first one. With those four conclusions, we can start to draw the shear and moment diagrams just by inspection. Now there's a few more things that we need to look up or look at. So these are some rules. We're going to want to draw that diagram from left to right. Okay, so just like you read from left to right. And all of these rules, once you get really comfortable with these, you can start to break them. Sometimes if there's something I don't want to deal with, I will draw the diagram from left to right, and then I'll come back and go from right to left, so I can get it done without having to deal with a particular point. But you have to be really careful when you start to break the rules. All right. So we're going to draw from left to right. We're going to start and end at 0. Okay, so just like balancing an account or something like that, we're going to start and end at 0. So we start at 0, we got to end at 0. So when you do your quiz, if you get back to 0, you know you got it right. Okay, now sometimes you can have a little bit of a round off or something like that, but you should get close, very close to 0. Theoretically, you'll get back to absolutely 0. The other thing is, how do you deal with concentrated forces? So concentrated force. If I have a concentrated force, if it's an upward force, it's an upward jump on the shear. If it's a downward force, it's a downward jump. So those forces are only shown on the shear diagram. They don't appear directly on the moment diagram. Now, concentrated forces change the reactions, and the reactions can change the moment diagram, so they do effectively change the moment diagram, but they don't show up directly. So I'm drawn from left to right. I'm starting and ending at 0. If I have a concentrated force that's pointing up, I jump up on the shear diagram. If I have a concentrated force that's going down, I jump down on the shear diagram. How much do I jump? I jump the magnitude of that force. And we want to think of everything as forces, not just the loads that are put on there, but the reactions. Those are really just forces too. So the fourth thing is concentrated moment. So with a concentrated moment, if it is a clockwise moment, is an upward jump on the moment. If it is a counterclockwise, it is a downward jump on the moment. So if we come to and these don't happen very often, but that can kind of be a problem because you don't think about them that much. But if we have a concentrated moment that's clockwise, we're going to jump up on the moment diagram according to the magnitude of that moment. If we have a concentrated moment that is counterclockwise, we're going to jump down on the diagram according to the magnitude of that moment. Oftentimes you get those with reactions. So let's take those 4 conclusions we came to in our derivation. 1 conclusion, 2 conclusion, 3 conclusions, 4 conclusions. And our rules work from left to right, start and end at 0. Concentrated forces cause jumps in the shear. Concentrated moments cause jumps in the moment. And put this all together and see how quickly we can draw those shear and moment diagrams that we did before. So if I look at what we had started last time and then finished up this time, where I have a concentrated load of P located here. And we've got the reactions, and there's no shortcut to getting the reactions. I'm not going to belabor the reactions. You should be able to get those. You've got to get them correctly. This would be P divided by 2. This would be P divided by 2. Okay? So let me be real clear on that. You got to spend your time. You've got to get your reactions. This is all for naught if your reactions aren't right. So you get your reactions, and then you can do the shortcut. So what's the shortcut going to look like here? Well, I've got my shear. I start at 0. Start at the left-hand side at 0. And then what do? I immediately encounter a concentrated force. Which way is the force pointing? It's up, so I jump up. How far do I jump up? The magnitude of the force. So I jump up, P divided by 2. And then what's going to happen? Well, a lot of people like to think, well, there's nothing here, so I have to jump back down. No. Okay? You jump up, and you stay there until something else happens. So we get to here, and then what happens? We jump down. So if we now are sitting at P over 2 and we jump down P, where is that going to place us? Should place it as at minus P over 2, right? If you're at P divided by 2, you subtract P from it, you get minus P over 2. And you just stay there. And then what happens? You jump back up again. If you're at minus P over 2 and you add P over 2, what do you get? 0. Good news. We got that right. Okay. So then with the shear, not the shear, the moment. I got W. Didn't make an M. So here is our moment. Okay, and again, if we had numbers, those would have units. We'll work some problems with some numbers, but I think it's important to look at these general trends. We start at 0 at the left-hand side. I don't have any equation. All I have is what I've got on the sheet here. I know that the moment changes by what? What do we have here? The change in the moment was equal to the area under the shear. So what's the area under this thing? Well, P divided by 2 times this distance, which is L over 2, gives me PL over 4. So I go from 0 to PL over 4. How in the world do I get there? Well, I know that the slope of the moment is equal to what? The value of the shear. So what value in the shear do I have? I have a constant positive value. So what's my slope going to be? Constant positive slope. Then this has an area. What's that area? It's going to be minus P over 2 times L over 2, which is minus PL over 4, right? If it's below the line, it's a negative area. That's a little, seems kind of odd, but it would be a negative area. So if I'm at positive PL over 4 and I subtract PL over 4, that takes me back to 0. How do I get there? This is a constant negative value. So what's my slope going to be? Constant negative slope. Okay? So once we get the reactions, and getting those reactions is important, it does take some time, but once we get the reactions, we can draw the shear and moment diagram in moments, less than a minute. You can zip right through that. Now, a lot of people might say, well, you don't have an equation, so yeah, you know these maximum points, you know this point. They're not going to disagree with that. But what if you wanted to know about this point here? You don't have an equation, so you can't get that. And I would say, well, no, I could get it. What would I do? I would just find that area there, wouldn't I? So this is a powerful tool. It's a quick tool and a powerful tool. Well, let's try the questions on that. Let's try the other one, the distributed one. So we got 8. How many pages did we get in electrical? Like 13 or 15 with the hour-and-a-half lecture? Quite a few. So I guess incidentally, this time I'm only going to run here for a few more minutes and finish this up. And normally, probably this time period won't go this long, but the first week, I assume there's probably not going to be a lot of questions on homework and whatnot. But bear with me for a few more minutes here. So we've got the other problem that we tackled, that distributed load. And again, you got to get the reactions. There's no shortcut to that. There's no easy way with that. So we said this was WL over 2, WL over 2. The length of this is L, and we had this distributed load up here, like this. And we wanted to come up with our shear and moment diagram. So there's the shear, there's the moment. Okay, I start at 0. I jump up, WL over 2, right? And now we get to use a different one, don't we? We get to say, let me get these handy here. We get to say that the change in the shear is equal to minus the area under the load. So this load was W, so the area under there is W times L, right? So if I stick a negative sign on there, I have minus WL. So if I take WL over 2 and I subtract WL, what's that give me? Minus WL over 2, right? So I know I'm going to end up at minus WL over 2. How do I get there? Well, I use this. The slope of the shear is equal to minus the value of the load. Slope of the shear is minus the value of the load. What slope do I have on, or the value of the load is a constant positive value, isn't it? So you take a constant positive number and you put a negative sign in front of it, what do you get? Constant negative. So we would have a constant negative slope, like that. Now you might say, well, you don't know where that crosses, and I would agree, but I can get it because I could say, well, this distance is x, so this is L minus x, right? And by similar triangles, I could say that WL over 2 is to x as WL over 2, the distance there, is to L minus x, right? So you come up with that ratio and proportion. because these triangles share this same angle. That angle and that angle is the same, and I'm saying that they are similar triangles in a mathematical sense. I mean, they obviously look similar, but they are similar triangles in a mathematical sense, and by ratio and proportion, we could solve for x, and it would turn out to be equal to L over 2. So that becomes important then when we go down there. So now with the moment, I don't have any concentrated moments. We'll do an example next time we get together with a concentrated moment. But if I start there, start at 0, the left-hand side, what do we know about the moment? It changes by the area under there. What's the area of that triangle? We had WL over 2. We had the distance L over 2. That's why you want to know this. So WL over 2 times L over 2 times a half, because it's a triangle, is WL squared over 8, right? So WL squared over 8. And how do I get there? The slope of the moment is equal to the value of the shear. The shear starts out at a large positive value, right? So I should have a large positive slope. Then it goes to a small positive value, so I should have what? A small positive slope. Just like that. Now I could do this triangle here and it'd be exactly the same except for negative, so I would subtract it off. It would take me back to 0. Starting to have some confidence in my answer. I think we can get this thing landed. We get back here. What's the slope here? Small negative number, so I have a small negative slope. Large negative number, so I have a large negative slope. There we go. And again, someone might say, well, you don't know the equation of that, so is it any good? Well, if I want to find the value of that there, that moment value right there, if I could come up here and find the area under this trapezoid, I should be able to get that, shouldn't I? Yeah. So it's a very valuable tool. Questions with that? Well, as we get more comfortable with shear and moment diagrams, we can tackle more and more real-life problems. And I wanted to bring in this interesting and unfortunately tragic real-life problem. It's based on the worst structural failure in U.S. history. Happened at the Hyatt Regency Hotel in Kansas City, Missouri. There's, of course, Kansas City, Kansas. There's Kansas City, Missouri. But it happened in July 17th, 1981. Like I said, Kansas City, Missouri, and actually killed 114 people. Now, obviously, more people died in the collapse of the Twin Towers, but because of how that happened and whatnot, usually that's not considered a structural failure. This was indeed a structural failure where something was built, it was being operated as it should be, and it just fell down. And what was going on with this was they had essentially two buildings, a building here and a building here, and at the second floor, this is the second floor, and at the fourth floor, they had a skywalk between these two buildings and an atrium area, and they had party down below here where people could dance, a big ballroom and whatnot, and then these skywalks where people could walk across. And obviously a ballroom with a post in the middle, swing your date into a post, that's not good. So they supported this. They came up and attached this to the roof and hooked the skyway for the fourth floor with a rod to the skyway on the second floor and supported it that way. And what happened is a failure right here. So if we look at this joint right here, we've got a couple of cross sections here, and it took them a long time, many years to sort this out. There was all kinds of speculation that people were dancing up here and it set up a resonance and things like that. But in the end, it was really just a poor design and really not properly understanding shear and moment diagrams. So if we look at what's going on at this connection right here, this was the original design. So we've got the original design here that I've got sketched out. Looks like I've gone kind of from an orthographic to an isometric, but I think you'll get the idea. So this direction along here is the direction that we see here. So this would be, people would be walking across this floor surface here as they went from one building to the next, and you would have these supporting beams that are then supported with this collector beam. And the original design had this rod that was coming from the roof and would come through this beam here and then have a nut and a washer, and that would continue on down to support this one down here. Okay, you can see some problems with this original design. You'd have to thread this nut up almost 2 stories of rod, so 20 or 30 feet of rod, and that's going to be problematic. So they built it a little bit differently, something that would be quite a bit easier to build. This is the way it was built. They had a rod that came from the, supported from the roof, came down here. You had then a nut and a washer go through this thing, and then here another nut to a rod that went down and supported the lower skywalk. So the way this failed is it failed in shear right through this surface here. Okay, so let's look at that. Let's look at that with a shear and moment diagram. So if I look at a model for this beam here, let's say that we have something that looks like this, and I'm going to have some load on this. Why don't I say that this is W. So I'll say that I have W there, and we'll say that we have some length there. And then, of course, we would need the reaction here, support holding this up. So we would have, what, WL over 2 and WL over 2. So then if I look at the shear, and I'm not going to draw the moment, I'm just going to draw the shear. But if I look at the shear diagram, over here, we would jump up WL over 2, and then we would decrease by the area under here to minus WL over 2, and that would be our shear diagram. And our maximum shear would be, of course, WL over 2. So that's for the original design. Now, if we look at the as-built, what does this look like in terms of a shear and moment diagram? Well, let's look at that. We're going to start out with this similar beam here. So this is, again, this beam that's going in and out of the page in this view up here. And we'll have to have these supports here. And we've got this distributed load. This would be L. This would be W. The same thing. But remember, you've got these rods down here. I mean, this is, again, coming down to something like this. I mean, this would be WL over 2, wouldn't it? So I'd better put those in. So I have WL over 2, and here I have WL over 2. And then the reactions, let's see, if I have WL over 2 and then WL over 2 from this, the reaction here is going to be what? WL, isn't it? And this one would be WL. So if I draw the shear diagram here, and again, I'm not going to worry about the moment diagram, but if I draw the shear diagram, what happens? It comes up to a value of WL, doesn't it? And for a little distance, whatever distance there is between these two rods, and then it drops down, WL over 2, and then it goes down like this, and then like that, where we have a minus WL over 2 and a minus WL. So then with that, what's our Vmax? Is equal to, of course, WL, which is twice what it was designed for. And this is one of these odd cases where it actually failed in shear. Oftentimes people are more concerned about the moment. We haven't even drawn the moment, or deflection. We'll talk about the deflection later. but it failed in shear. Okay, and we're into this, what, a couple hours of lecture, and we can recognize this, and tragically, no one recognized that. It ended up killing 114 people. So there's certain things that if you don't take care of carefully, if you don't do right, people are going to die, and that's an important thing to remember, an important thing to make sure that you don't get caught up in something like this. There's a lot of things that we do in engineering that, no matter how they mess it up, it's probably not going to kill someone, probably not even going to be a problem, but there are a few things that you got to do right or people are going to die. And there's a lot of argument through the analysis of this in terms of who inspected it and who did the design, who changed the design. But in the end, if you're the engineer that came up with this original design, one, you came up with a design that you were just begging someone to change because it's very hard to construct, and two, you should have made sure that they paid you to go out and inspect the design and see that it was built the way that you had actually designed it. So make sure you're checking on those things, and make sure that you're coming up with designs that are easy to build, so that you're not tempting people to do something like this. Because in the end, you're responsible, and a lot of people lost their lives, and they really shouldn't have. This is a very simple problem, but had a very tragic result. So gives you a little more to think about when you draw shear and moment diagrams. Well, I will leave you with that. Like I said, a good problem, a real problem, and unfortunately a tragic problem. I'll talk to you next time. Take care till then.